So before we begin, I want to go over quickly the properties of gases that we're going to be talking a lot about in this unit. So we can use these different properties to predict how a gas might behave. So if one of these variables are altered, we can see how that gas might act as a result. So those are temperature, volume, and pressure. So temperature is a measure of the average kinetic energy of the particles within a substance. So the higher the temperature, the higher the average kinetic energy. Or if the lower the temperature, the lower the average kinetic energy. So remember, this kinetic energy is the motion of those particles. So how fast are the particles moving is what temperature is telling us. So if we look in this video, you can see that I'm applying heat to this sample. And as I do that, the particles are starting to spread apart and move a lot faster. Okay, they're picking up average kinetic energy when heat is applied. Okay, thus it's increasing that temperature. So pressure is created when gas particles collide with the surface of an object. Okay, so this becomes important, especially for meteorologists when they are predicting the weather. Okay, because differences in the atmospheric pressure, whether it be low or high, is what is a big driving factor for what kind of weather that we're going to have. Okay, so the units are typically going to be in kilopascals and atmospheres, okay, for the purposes of this class. But there are different kinds of units of pressure like PSI or millimeters of mercury, etc. So if something has low pressure, if a gas has low pressure, that means that there are less collisions with the walls of that container or the surface of an object. Something has higher pressure, the more collisions that there are with the surface of an object or the walls of that container. So in general, more collisions equals higher pressure. Okay, so in simpler terms, we can say pressure is how fast or how frequent particles hit the walls of a container. So in this video, you can see that the pressure starts at around 23 atmospheres. Now I'm just going to add some heat to that. Okay, the heat is going to make the particles move faster and increase their average kinetic energy. Okay, when it does that, it's increasing the energy of the particles. They're going to be colliding with one another and with the walls of that container a lot more. Okay, so there's more collisions now. So we can see that that pressure went up to 153.5 atmospheres. So STP is standard temperature and pressure. We've talked about this a bunch, but this, if you forget, is always on table A. So for pressure, 101.3 kilopascals is equal to 1 atmosphere. And then just as a little review as well, these are the elements in purple that exist as gases at the standard temperature and pressure. Okay, so at 0 degrees Celsius and 101.3 kilopascals or at 1 atmosphere. So atmospheric pressure is the force exerted on Earth's surface by the constant collision of gas molecules in the atmosphere. So we're going to talk about atmospheric pressure a bit more later in the unit, but we know that on Earth we have the force of gravity that's pulling us down towards the center of the Earth. That's why we don't just float away into space. But if you compare somebody that is standing on the surface of the Earth to somebody that is standing on the top of a mountain, the person that is standing on the surface is going to be experiencing a higher atmospheric pressure because that's there's more particles down lower towards the surface of the Earth. Okay, if there's more particles there, the more collisions that there are, thus having a higher pressure. But as you go up in altitude and you start getting closer to space, the less and less gas particles that there are. Okay, so the less collisions there will be and the lower pressure. Okay, so to review entropy, entropy is the measure of the disorder in a system. So entropy will increase with increasing disorder of particles. So when we talked about our matter and energy unit, We said how solids have the least amount of disorder or the least amount of entropy. And as we go from a liquid to a gas, when the particles get farther and farther away from each other, it increases that randomness and it makes it more disordered. Okay, so gases are going to have the most amount of entropy. Remember, our systems in nature tend to undergo changes towards lower energy and higher entropy. So nature is always lazy and messy, okay? It's just how it likes to be. So the lazy meaning that low energy, okay? Particles rather be in the lowest, most stable energy as possible, and messy meaning higher entropy, more disorder. Okay, great analogy if you're ever in class and you're trying to remember what entropy means. Okay, Mr. Guthke's side of the desk would be considered an example of high entropy. Okay, there's a lot amount of disorder, it's less organized. Okay, whereas my side of the desk usually is a little bit more organized. So we can say that this is lower entropy or less disorder. All right, so into the kinetic molecular theory or KMT of gases. So we use this to predict the behavior of ideal gas molecules. So ideal gases are gases that are ideal, okay? They're perfect. So in a perfect world, in perfect scenarios, this is how gases will behave, okay? Exactly according to this theory. Okay, so the reason why this theory exists, is because it allows scientists and engineers to predict or control and manipulate the behavior of gases, okay, in different kinds of applications, maybe in engineering or in some industrial applications. So let's say an engineer wants to design and optimize an industrial refrigeration system or something like that. Okay, when they're planning to do that, if they know these basic assumptions of how gases will typically behave, okay, that'll help guide them to kind of figure out what they need to do to actually create that system. So the first assumption is gas particles are in constant random straight line motion. So gas particles would kind of look like in this diagram here. They're always going to be going in a straight line in a straight direction. Okay, they will not change direction unless they hit into something else. Okay, so you can think of them as like being the perfect bumper cars. The second assumption is gas particles collide with each other in the walls of its container, and this is what creates pressure, as we talked about. These collisions are known to be elastic. So elastic collisions means that there is no loss of energy. Okay, so in reality, energy is always going to be lost as heat or sound. Like, for example, if you have something like a super bouncy ball and you have it in your hand and you drop it onto the floor and it bounces back, okay, over time, that bouncy ball, it's not going to go back directly to your hand each and every time if you're holding your hand at the same height, okay, because some of that energy will be lost somewhere to the environment, okay, in the form of heat or sound or something like that. Okay, same thing with a Newton's cradle. Eventually, all of the steel balls will eventually stop moving, okay, because in reality, we don't have these elastic conditions. But the assumption that the kinetic molecular theory has is that these collisions of gases will always be elastic. So there's no loss of energy. They're perfect elastic collisions. Okay, third assumption is gas particles have no intermolecular forces of attraction. Okay, therefore, they do not attract or repel each other. So remember, intermolecular forces are the forces that are between, meaning between molecules or particles. So this is a diagram showing that intermolecular force between two hydrogen chloride molecules. Okay, but kinetic molecular theory states that the gases do not have these intermolecular forces. Okay, they do not stick to each other at all. So in reality, everything has intermolecular forces because all of our atoms and molecules are made up of charged particles. Okay, so there's always going to be some sort of attraction or repulsion. However, the KMT states that these gas particles will not have these intermolecular forces. Fourth assumption is gas particles have mass but no volume. They are very far apart from each other and relative to their size have volume that is negligible. Okay, negligible meaning that it doesn't really count, doesn't really matter, or it doesn't really affect anything because it is so small. Okay, so the empty space between gas particles is so large, okay, that the physical size of the atoms doesn't really matter. Okay, therefore it makes the volume negligible. Okay, the last and the fifth assumption is the absolute temperature, Kelvin temperature of an ideal gas is directly proportional to its average kinetic energy. So this is just saying that if temperature doubles, the average kinetic energy will double. Okay, so this is based on that kinetic molecular theory of an ideal or a perfect gas. However, in real gases, in reality, particles have intermolecular forces and they have a certain kinds of volume depending on how large the particles are. So temperature is sometimes not exactly proportional to the average kinetic energy, but the kinetic molecular theory says that it is. Okay, so now going over an ideal versus a real gas. So ideal gases is that perfect gas, okay? What the kinetic molecular theory of gases is actually referring to. Okay, so there are gases that act most like or most closely like ideal gases, and those are going to be in nature hydrogen gas and helium gas. Okay, they act most like ideal gases because they are very light. Okay, hydrogen is atomic number 1 and helium is atomic number 2. So they're the smallest, they are the lightest. Okay, so they're going to take up the least amount of space and have very low intermolecular forces. Therefore, it allows them to behave most like ideal gases in nature. Okay, remember that hydrogen is always in nature as a diatomic molecule, so two of the same atom covalently bound together, or H2. And helium is one of those noble gases, so it's always going to be monatomic or just single atoms by itself. Okay, so the kinetic molecular theory is not perfect, okay, because in reality, we have real gases. So real gas particles do not behave exactly as the KMT describes, okay, because of a bunch of different reasons. Some of it being by its increasing mass. So the heavier the gas is, the less ideal it is, okay, because the more space it takes up, and then also increasing intermolecular forces. Also, the increasing polarity, so more polar molecules will have greater intermolecular forces. Okay, so that's not because kinetic molecular theory states that the particles don't have intermolecular forces. If a molecule is more and more polar, okay, it will behave more like a real gas, not really an ideal gas. Okay, so for example, water molecules, which is a polar molecule, in the atmosphere attract each other when temperature is cold enough, and in upper atmosphere, rain or snow can form. Okay, so if this was not true, okay, where polarity and increasing mass didn't affect how ideal or real a gas was, there would be no intermolecular forces or things like that, so rain or snow would not be able to form. Okay, so real gases will behave most like or most similarly to an ideal gas when the pressure is low pressure, and when the temperature is high or high temperature. So there's a really easy way to remember this, and it is PLIGHT. So PLIGHT stands for pressure low, ideal gas, high temperature. So this is when a real gas in real life, in nature, will behave most like an ideal gas under these conditions. So low pressure, less collisions, and also a higher temperature, so more kinetic energy of the particles. All right, last thing is Avogadro's hypothesis. So Avogadro's hypothesis states that equal volumes of all gases under the same temperature and pressure conditions will contain equal numbers of molecules or particles. Okay, so look at this again. So we talked about the volume, pressure, and temperature being the three main properties of gases that are going to become important for this unit. So if volume, pressure, and temperature are all the same, okay, for any kind of gas, this hypothesis states that the number of molecules or particles in that sample will be equal to each other. Okay, so let's just think of this scenario. So let's say we have two balloons. One balloon is just exhaled air. Okay, so I just blew up this balloon, okay, with 12 liters of breath of exhaled air. So that's a combination of some nitrogen, some oxygen, some carbon dioxide, and things like that. Okay, and then we can compare that to a balloon balloon B of the same volume, 12 liters, but this is just filled with pure helium gas. Okay, so if these balloons, if the air, or rather, if the gases inside each of these balloons are at the same pressure, so they're each at 1 atmosphere, and they're at the same temperature, 298 Kelvin, okay, and we already said that the volume is the same. Okay, this means that because of Avogadro's hypothesis, the number of air particles in balloon A and balloon B will be the same. So the number of air particles in balloon A is equal to the number of helium particles in balloon B. Okay, so this is just that other picture blown up again. So this is showing a sample of helium gas, nitrogen gas, and methane gas. So they're all at a volume of 22.4 liters. They're all at a pressure of 1 atmosphere, and they're all at a temperature of 0 degrees Celsius. Okay, so the volume, pressure, and temperature are all the same for these gases. And even though their masses will vary, right? So helium will be a lot lighter than methane and then nitrogen. Okay, it doesn't matter. Because their volume, pressure, and temperature are the same, the number of gas molecules that are actually contained here, okay, are going to be exactly the same.